Heisenberg's uncertainty principle for a quantum particle allows its wave function to penetrate into a classically forbidden region, which we will see in the particle in a finite box. Consider now an electron in a potential well, where the walls are not infinite, but finite at a constant value V0. An electron with energy E greater than V0 is considered a free electron because it has sufficient energy to travel off to infinity. It would have a wave function like that of a free electron we found before. It would gain kinetic energy in the region of the well and speed up, having a more wiggly wave function there. Recall that this came from the wave-like solution to the Schrödinger equation, which required the second derivative to have opposite sign as the wave function itself, because E minus V is positive. The solution is an exponential with a purely imaginary argument, which gives sine and cosine waves. Here, k is a purely real wave number, but could be positive or negative. For E less than V0, but greater than 0, the electron is considered to be bound, because classically it always has to be in the well, bouncing back and forth. Inside the well, it should have a wave-like wave function, similar to that we found in the infinite well. Outside the well, in the classically forbidden region, with E less than V, we can flip the sign of both sides of the Schrödinger equation to see that now the solution is a wave function whose second derivative is the same sign as the wave function itself. The solution to this equation is now an exponential with a purely real argument. Here, alpha is very similar with the same units as wave number k, but describes exponential decay of the wave function instead of wave-like characteristics. Here we show the ground state wave function for the finite well. Inside the well, the wave function looks similar to what we found for the infinite well. The wave function there looks like a half of a wave. In the barrier, the solution to the Schrödinger equation is an exponential function with purely real exponent that is either positive or negative. Because the particle is not allowed to enter the barrier classically, we don't expect the wave function to penetrate the barrier very far, only about as much as its Heisenberg uncertainty in position. That means we expect the wave function to become zero at large distances into the barrier. Thus the wave function must have a positive exponent on the left and a negative exponent on the right. Any contribution from the exponential with the opposite sign is eliminated because of the boundary condition that psi should tend to 0 at infinity away from the well. The exponent parameter alpha describes the inverse of the penetration depth, or exponential decay length of the wave function in the forbidden region. The boundary conditions of the sides of the well require that the wave function and the first derivative of the wave function to be continuous there. This will give us a smooth wave function as it transitions from the allowed to the forbidden region. Only the curvature of the wave function changes from curving towards 0 like a wave in the allowed region to curving away from 0 like an exponential in the forbidden region, which comes from the Schrödinger equation. Here we solve the Schrödinger equation mathematically for a bound electron in a finite potential well. We divide the problem into 3 regions, where the potential locally is a constant in each region. The Schrödinger equation is a second-order differential equation, so we expect 2 unknown constants that we need to solve for using the boundary conditions. For example, in the forbidden region 1, we saw that the solution for an electron, where E is less than V0, is an exponential with exponent alpha, where alpha squared is determined by V0 minus E, so alpha could be positive or negative real number. We can write the general solution with some as yet unknown constant A1 for the plus alpha exponential and A2 for the minus alpha exponential. The boundary condition that requires the wave function to go to 0 at x equals minus infinity requires that A2 equals 0 because e to the minus alpha x becomes large at x equals minus infinity. E to the plus alpha x itself goes to 0 at x equals minus infinity, so that boundary condition does not put any constraints on A1. In general, we expect that each boundary condition to remove one unknown. Similarly, in region 3, we expect that the wave function to be e to the minus alpha x exponential, because here the wave function should become 0 at positive infinity. In region 2, the solutions to the Schrödinger equation are plane waves like a free electron where the wave number of the electron is determined by the kinetic energy, the energy above the potential E minus V, where V equals 0 in region 2. This gives us unknown constants B1 and B2 for each of the plus K and minus K solutions. The boundary conditions between the regions should constrain the energy and reduce the number of unknown constants to just one. That would be determined by the wave function normalization like we found for the particle in an infinite box. The boundary condition at x equals 0 are that the wave function and its first derivative should be continuous. This means a1 from region 1 is simply equal to b1 plus b2 from region 2 because the exponentials at x equals 0 are all 1. For the derivative to be continuous, we bring down the exponent to give us a1 times alpha at x equals 0 equals b1k minus b2k. At x equals a, the boundary conditions are similar, but the exponentials at x equals a are not equal to 1, giving us this equation with b1 and b2 being related to c2, and the continuous derivative boundary condition brings down a k and a minus k in region 2 and a minus alpha in region 3. In principle, we now have enough equations to solve for all the unknowns. The algebra of these linear equations is straightforward using linear algebra, but time-consuming to do by hand. Traditionally, physics problems like this are greatly simplified after recognizing some trick that simplifies the algebra. In this case, recognizing that the problem has a center of symmetry greatly simplifies the algebra. For example, the center of symmetry further constrains region 2 and requires that region 1 and 3 be related by symmetry or antisymmetry. This is done mathematically in the example in the book and left as an exercise. Keeping in mind the symmetry of the problem and the solutions to the particle in an infinite box, we can get a good idea of what the finite potential well solutions should look like. The lowest energy or ground state wave function should look like a half wave with no nodes. Once the wave function enters the barrier, it decays exponentially. The first excited state should have a single node in the center of the well with an antisymmetric wave function that changes sign at the center. Again, the wave function exponentially decays to 0 on both sides after entering the forbidden region. The next higher energy state has 2 nodes in the well and exponential decay in the forbidden region. States with a higher energy E will have a smaller alpha and therefore a larger penetration depth, as seen in these 3 examples. Each wave within the well doesn't go to 0 at the boundaries like it did in the infinite well. This means that the wavelength of the wave function is actually larger than the width of the well. This implies that the energy E of the wave function is less than that for an infinite well of length A, because in the finite well, the wave function is less confined, like it's in a larger box. Such quantum wells can be fabricated in the laboratory using thin film deposition of semiconductors. For example, it is possible to make a 2 nanometer thick film that makes a 0.5 eV well for electrons traveling perpendicular to the film. In this case, the electron wave functions along that direction becomes quantized for the 3 lowest energy states. The wave functions look similar to the first 3 particle-in-a-box wave functions, but their energy is reduced because they can penetrate some outside the well. Wave functions can have any energy higher than 0.5 eV, representing free electrons. The quantization of energy in quantum-confined states enables precise energy selection. Electrons can only absorb or emit a photon transitioning from these exact levels, making the photon wavelength precisely controlled by the size of the quantum well. Such quantum well-based lasers enable the precise transmission of optical signals that carry most of the information on the Internet.